Yeah. So I really appreciate Professor Lina hosting me here, and it's such a great honor to speak in this conference. Today I want to talk a little bit, over the past 10, 15 years, what happened in AI and why I'm so optimistic about the future of AI. And so currently I work at OpenAI, and my team focuses on multimodal and reasoning. And I want to insert an ad before we go into the talk. And over the past week, a few people in my team actually trained a model for the advanced voice mode. If you don't know that, you can open ChatGPT. And if you don't have that, please download it. And then you can click on that black button that goes to the voice mode. And also, there's a video feed. You can ask anything that you see. And hey, can you tell me a joke about Harvard? I'm currently giving an AI talk here. It should be appropriate, okay?
Absolutely. It looks like you've got a fun crowd there with all those colorful seats. Here's a Harvard joke for your talk. Why don't Harvard students play hide and seek? Because good luck hiding that Harvard pride. Hope that one gets...
Okay, that's not bad. That's not bad. Okay, let's go back to the talk. And that's all real time. Let's give it a try. It help a lot of people. And, I learned many cases, like ChatGPT actually saved people's life. I have a friend who uploaded their whole medical history to ChatGPT, and they diagnosed something that the doctor never diagnosed. And actually, that's the right diagnosis for their patient. And so it's just amazing to see things like that. So this talk, I realize I have too many slides and also too technical, so I will probably skip something. And if I'm going too fast, please stop me. This all started about 70 years ago, right? And basically Turing asked the question, can machines think? So one key thing from the paper I got out is when we say can machines think, we're actually not trying to build a machine that mimics adult's brain. We're actually trying to build something that mimics infant's brain and give a course of education to that model. And that's a key difference between many branches of AI. And this particular philosophy that I strongly agree with. This will come back again and again in the talk. And so there's three parts to the talk. The first one, I want to review the history. It's basically a tale of two cities. One is self-supervised learning, the other is reinforced learning. And then I want to talk about the open problems we're facing now. And the third part is I want to see, imagine what's going to be the future. And let's go to the first city, the self-supervised learning. So neural net has been there for like 30, 40, 50 years, right? It's been there a long time. But the current wave of revolution begins in 2012, where the AlexNet actually achieved really good result on ImageNet. So basically, the insight from AlexNet is with a lot of data and compute, this neural network can beat decades of hand-engineered vision algorithms. So that year was a lot of people has been working on hand-engineered vision features for like decades, and they felt really sad because all their work just beaten by data and compute with a simple architecture. And this theme is going to come again and again also. This also maps to Turing's point. We're not trying to give our human inductive bias to the model. We want to build a structure that the model just want to learn, right? And then 2013, there's a famous paper from Google, the word-to-vec. Basically, it's a really good representation of words from training. And then there are two things happen from that. One is then everyone want to build everything to vec. You can, when you do the app recommendation, like when you go to App Store or Google Play Store, how they do the recommendation to you is they embed each app to a vector. And then based on the vector, the distance between different apps, they can recommend you apps. And they want to embed every advertisement to a vector. They want to embed every video to a vector. The YouTube videos you see, they're recommended by representations like this. And the other thing is actually, again, showed compute plus data is much more effective than inductive bias. Like for decades, people have been hand-engineered features in NLP. They don't matter that much anymore. And if people here who has worked on that, I'm sorry to say that, but that's the truth. And then 2015, Adam came up, right? It's just an optimization algorithm that standardized a lot of things, so that significantly accelerated the development of deep learning. And you don't have to hand-tune a lot of parameters, and it's pretty robust across different data sets, especially with noisy and sparse gradient. Even right now, a lot of the optimization algorithm is just variations of item in the large language model era. So then, not far away from here, I think this is Kai Ming's paper, the ResNet, right? And the way I interpret ResNet is it's kind of an ensemble of a lot of different types, the models of different types. The left side is this is the area surface of the deep neural net without the residual connections. And this one, I think this is the left side, or right-hand side for you. And it's with the ResNet. You can see the loss curve is much smoother. That's much easier to feed. And this actually solved the long-lasting problem that we cannot feed super deep neural net before. Now you can feed hundreds of layers rather than a dozen layers. And this is also becoming the standard architecture of many of the state-of-the-art models. Then I want to talk about when I was in the industry, I had a lot of fun, and because we know the feeding a neural network is a non-convex optimization, right? And what happens to non-convex optimization? You're stuck in a random local minimum. And that gave me a lot of fun, and a lot of people, right? So a few things actually ease that fun for me. One is, I think a lot of intuition from 3D work is just misleading. When I learned statistics, it's actually relatively low-dimensional statistics. A lot of the intuition there actually wrong. When you have a trillion dimension, it's just really hard to stuck in a local minimum. You have so many degree of freedom to escape from that local minimum. And then the second point is there are a lot of empirical studies of the data on NLP and images, basically telling us, even though there's a local minimum, it's a very flat and very nice one, and it's not so far away from the global minimum. So this part basically go away. Everyone is saying non-convex optimization, so what? It works in practice. And the other part I have is, traditional statistical model. I think I learned too much math, and they tell you, when you have number of parameters greater than the number of data points you have, you can feed any random label, right? There's no point in building a model like that. And then, like in the deep learning world, you are way over parameterized. Your number of parameters are way higher than the number of data points you have, right? So that didn't lead to overfit. So there are a series of studies. The gist of that basically is people found out the stochastic gradient descent is actually a really good compressor. Those compressors actually learn the patterns first. Like mathematically, when you do a eigenvalue decomposition, right, they will learn the eigenfeatures of the largest eigenvalue first, and then they learn the smaller, eigenvalues, and then they learn the noise. So even if you are over parameterized, it's okay. If there is any pattern, they will learn the pattern. So that eased my thought about over parameterization. By the way, a lot of them are just personal worries and so on. I from a pure math background, I tend to worry things more theoretically before, but in practice things just work. It's amazing to see. And then those are the more theoretical background why that works. Then from 2014 to 2016 is the era of the recurrent models. The RNN took off. And we have really amazing translation models based on RNN. One challenge, though, that didn't solve is it's really hard to train large RNNs because it's hard to parallel the RNNs because it's recurrent. You need to, in every training, you need to train one step and then the other step, right? And so this relates to the hardware and software co-design. When you have GPUs, you can parallel so many things, so you want your model to be parallelizable as much as possible. And the second thing about RNN is they suffer from gradient vanishing. Remember the ResNet solved the issue that you can train really deep neural nets? Here, the gradient vanish on the time horizon. You have too many time steps, the gradient starts to vanish. So those are two key issues that didn't get resolved really well. And then next year, Transformer is born. This is the backbone of most state-of-the-art architectures. Basically, they combine attention and then the feed-forward layers, then stack them together. It's very data efficient, and this architecture become the backbone of nearly all cutting-edge NLP models right now, all multimodal models. And So in the initial paper, it's for translation. So it's a encoder and decoder dual tower model. And currently people only use the decoder part just for simplicity. Again, like back to Turing or maybe to Rich Sutton, you want as little inductive bias as possible. You just want a really simple model and feed the model with compute and data. And then scaling law came because of not because of transformer, because we have transformer, we can study those scaling laws very effectively. There's a GPT-2, GPT-3, and 2020, and there is a scaling law plotted. This is really, this is empirical law. This is not the Newton's law of motion or anything. But if you look at the laws and the compute data and parameters, it's super log linear. So when you have more compute, you can achieve lower loss. When you have more data, you can achieve lower loss. Like you have more parameters, you can achieve lower loss. And this is really amazing. This is really a beautiful thing to see, right? And then this gives people a lot of, it's almost to many people in Silicon Valley, this is a religious belief that's going to hold. And so this is another point. This is auto distribution data prediction, right? So scaling law was 2020, GPT-4 is 2022 to 2023, right? This law almost perfectly predicts the performance of GPT-4 on perplexity. And so this, it will not always hold. There will be always plateau or things like that. But scaling law right now already spanning across 13 order of magnitude. And that's a huge number. Going forward, so coming back to the beta license. This is a bit, if you haven't read the beta license, please read it. I have read it like 10 times over the past several years. And every time I read it, I get new reward from reading it. And so we have been coming back to this more and more, right? The gist of this is general methods that leverage compute ultimately outperform those relying heavily on human engineered inductive biases. So I know a lot of researchers, scientists, they want to, imbude their own, experience into the model, into anything they do, right? But in machine learning or in AI, that's actually a bad thing to do. You want the model to be as naive as possible and feed them data and feed them compute, rather than put your human prayer into them, and that's a bad thing. And the two methods that scales arbitrarily well with data and compute is search and learning. And we have been focusing on learning for the past 15 minutes. And the next one, in the next part, we're going to focus on more on search. The other thing is I want to, this scaling law is also something make you wonder where does this coming from, right? As scientists, you have this curiosity. I don't trust anything just you observe. I want to understand things one level deeper. Where is scaling law coming from? One explanation I found out very satisfying. I don't know, this might not be 100% true, but a lot of people hypothesize scaling law actually coming from the structure of the data. Remember what we said before, SGD, the stochastic gradient descent, actually learn the eigenspace of the largest eigenvalue first, and then the eigenspace of the smaller eigenvalues, right, and so on. So then if your data has a power law distribution, then your learning will have a scaling law distribution, right? And this is the difference between, like, the hypothesis is higher intelligence data is exponentially proportionally has lower volume on the internet, which more or less is true, right? Like there are so many books on arithmetic, but there are only maybe a few good books on algebraic geometry, right? So there's that power law distribution is really what's driving the scaling law. And the other thing is common disease versus rare disease. There are just a lot of cases for rare disease, for common disease, and there are a few very tiny amount of data for rare disease. So that's why, mediocre doctors can diagnose common diseases, right? But really good doctors can really treat the rare disease. This is a similar thing in the model learning. And the other thing people wondered 2-3 years ago, I think people stop wondering now, is why the smoothing scaling law actually lead to discrete emergent abilities. When I say discrete, I mean once you reach a level, the model suddenly can do something. For example, the model suddenly can do math. They can suddenly, do a lot of medical diagnosis, right? You don't see a smooth curve. The reason I think goes back to the learning is when the model learn, they try to grok one thing, and when you reach a certain amount of compute, and basically corresponding to the eigenspace or the order of magnitude of the eigenvalues. And so going back, what we have now, and like from history at that point, is we have a scalable architecture with a decent scaling curve, and that's what we had. And then Ilya has a famous saying, right? The models just want to learn. And that means the model has a simple structure, just feed them with compute and data, and then you observe they just learn. That's just amazing. And then another thing, a lot of discussions, I think also a few years ago, does compression or prediction really lead to understanding? A lot of people has a lot of thought about it. And I don't know 100%, but more and more I believe that is the case. Like if you look at from information theoretical perspective, Shannon said information is linked to unpredictability. If you can predict something perfectly well, that means you understand that thing, right? It doesn't surprise you anymore. And you can do this mind exercise. If you can predict what the other person, maybe your PC or either, right? Maybe your girlfriend or boyfriend, what they say exactly in the next sentence, you're sure you understand that person really, really well, right? And the other thing is, so intelligence, they want to see is a reduce of surprise by modeling patterns, and we can see the LLM actually they grokking the patterns gradually, like grammars, facts, common sense reasoning, and so on. So this is very aligned with information theoretical perspective. Is prediction and compression is understanding and intelligence. From the cognitive science perspective, we as a human being has been trying to compress the universe for many, many centuries, right? And then we will compress, for example, the Newton's law of motion. They observe a lot of data, and then they compress that vast amount of data into laws. And in neuroscience, like people discovered, our brain is also constantly compressing sensory input. Like for example, if nothing surprising is happening, it's all in compression. You don't react to that. But like once there's anything new, your brain start to react to that. The theory behind this is that actually why, as people get older, they think the time goes by faster. The reason for that is because if you're repeating your day and day, your brain tends to compress those time into a very small amount of information. That's why to a kid, like a 1 year is a long time, but as I grow older, which is very scary, is 1 year seems really short because you're sleeping in the office every day, and you don't see the different things. So that's another thing about compression. Then let's go to the second city, the reinforced learning. So this is a history a little bit cleaner. So there are two main branches that I follow. One is DeepMind. So 2015 there's DQN, and it's the first time we combine deep learning and reinforced learning, and you can actually play Atari games really, really well from just raw pixels. And I had a lot of fun watching those videos, and I call them a kind of alien intelligence because they're just so much different than human. They find all the hacks in the games that I never. So as a kid, I played them growing up, but there are a lot of tricks I never discovered myself. Then there's AlphaGo. That's the big news. So it's bootstrapped with certain number of human data, and then did a lot of self-play and Monte Carlo tree search, and defeated the world champion, which is a landmark AI achievement. So I think that's a big moment if you were paying attention to this at that time. And then there's AlphaGo. One thing that's fascinating is self-play. I don't know, there's also a lot of kung fu novels when I was growing up, and I read them. And in one of the novel, the author said, this person is so good at kung fu, he doesn't have anyone can beat him. So he started to self-play. He basically split the brain and the body. He will fight from left to right, and that way he practiced to get better at kung fu. And that's exactly what AlphaGo does. They will they will train the model, and they will put them into two different servers, and they play games against each other. And then based on that, they will train another model, and go on, right? So this analogy is fascinating in many ways. Am I talking too fast? No? Awesome. Then there's AlphaGo 0. So basically, they get rid of the human prayer and train the stretch from the data. One thing that's surprising to people, we will come back to that, which is Mu 37, when he's playing with the world champion, and that's actually out of the human distribution. Like every Go expert said that's a really bad move, but actually it's a really great move discovered by AI. And then there's Alpha 0. Basically, they extended the board game to chess and shochi. And then they got bored at board games, and they're starting like 3D video games and mastered Alpha Star. And another branch of folks is Berkeley to OpenAI folks. So John Schumann have this TRPO, this trusted region proximal optimization. And basically, they address the instability issue by having a KL divergence between old and new policies. So the new policy cannot diverge too much from the old policy, which enforce some kind of stability. And there's PPO, which is an upgraded version of TRPO, and PPO is behind the ChatGPT. The ChatGPT post-training is mainly on the RHF. The RL part is mainly by PPO. And then there's OpenAI also joined the race on video games. They played Dota 2 rather than StarCraft, and they also achieved the world championship at Dota 2. But then one key question remains. Those are really impressive RL, achievements, right? But they had little economic value, like their games mainly. And the reason is there is no, economically valuable, generalizable prayers or environment. They're specialized AI. I call them specialized, super intelligence. They're much better at human at this certain thing, but they're not general intelligence in any way. So that leads to the merge of these two cities, pre-train plus RL, and makes things super, super useful to everyone. So the first paradigm I call the pre-train plus low compute RL is basically from the InstructGPT and ChatGPT. So basically, you have a pre-trained model, and then you have a small amount of compute on top of that using RHF, and that becomes super, super helpful. And it was a surprise to even OpenAI people who build this. It's called a low-key research preview, and built by John Shulman, Barrett, Luke, Liam, and now it's way over 500 million users use ChatGPT every week, and it's growing very, very fast. So the world starts to see the value of those models, the intelligence. And this is how different steps are RHF. We will not go into details like that. It's pretty straightforward. And so what changed from the game RL? Everyone was into games, right? The board games and video games and so on. The thing that changed is we have a much more generalizable prayer, which is the language model. And the language model encodes most of the human knowledge we developed over the last thousands of years. And currently, the majority of the generalizability coming from the pre-train, not the RL part yet, because RL is pretty, sometimes can be mode seeking, sometimes you lose a little bit entropy, and so on. So I think that's the limitation. And there's an illustration of this called the Young LeCun cake. And he's saying, the good model, you spend a lot of time on self-supervised learning or compute, that's the cake itself. And then you have supervised learning, which is SFT, and they call that the icing. And then you have the cherry on top, which is pure RL. And I don't think that's a good thing to have. And I believe you really need even more RL, more computing in RL than in pre-train to achieve AGI or ASI, because that's how humans learn. We spend, most people here are researchers, right? You spend most of your time doing research rather than learn things. And that's my personal belief. So also coming back to beta lesson, and Sutton mentioned, sorry I repeat things a lot, but if you haven't read it please. So there are two main methodology that scale really well with compute, right? One is learning, the other is search. We scale the hell out of learning already, let's scale the hell out of search. And which is a paradigm 2, this pre-train plus high compute RL. And so OpenAI started this last year by releasing O-series models. And we started the next paradigm of scaling called high compute RL and test-time compute. Then there's a open source alternative called DeepSeek R1, and it was in the news for 2-3 weeks, just every day I see news. And you can see with more test sample compute, anyone took AMI in this room? Most people, right, to get into Harvard. And you see the AMI score from like 20% to like 80%, and with more test sample compute or RL training, which is amazing. I mean, AMI is not trivial. It's not that hard, but it's still a non-trivial math. Then let's call this, I call this a new paradigm. Rich Sutton and David Silver has a new paper months ago called Welcome to the Era Experience. And it's very well written. Basically, the core idea is the high-quality human data actually is limited. And I had a very emotional Twitter post for the new year, for this year, like January the 1st. It got kind of viral, so I deleted it. And the emotional part of that is, if you think about this, like human has been preparing for this AI or AGI for thousands of years, right? We invented printing press to record our intelligence, and then there's computers, there's internet, and that accumulate a huge amount of data for AI to learn. If without the computer or internet, there will not be AI, and maybe there's just natural evolution, right? The silicon intelligence is going to be the next intelligent thing. So then you ask, but then we already mined most of the human data. So what do we do next, right? For AI is then we think about where does human data coming from? Human data coming from how the human brain interact with the environment. We think and we do something, we get the feedback from the environment, and then we adjust our learning, adjust our beliefs, adjust our ways in our head. And we want to do the same thing for AI. So basically, in the far future, you can think of energy, compute is going to be almost zero. It's abundance. You have infinite amount of compute. What's limiting us fundamentally is data. But if you can convert compute similarly to how you convert the human brain compute to data, then you have a self-enforcing loop. And that loop can be much faster than how human evolve. This is just an anecdote why the reasoning part, why chain of thought works. The fundamental reason is it doesn't make sense to spend equal amount of compute on each token. I think that's the past. That's the first part of the talk. I want to see how I'm doing on time. I'm doing good. So personally, this is a journey where I, from skeptical to AGI-pilled. And I know it's just a big word, but I do think, this is a hot take, I do think most of the society still underestimate how important or how impactful AI is going to be. Like AI is different than other technologies. AI is going to fundamentally change science, change the society. And inventing internet is great, but that's not at the same scale as AI. So I had a lot of fun, from a more pure math background. I doubt everything, basically, unless you show me the proof, right? That's not a good mindset to have. I think my brain was a little bit overtrained for that. And there's a lot of fun, non-convex computation, over-parameterization, also what is understanding that's prediction leads to understanding, and so on. I think the biggest fun for me, the biggest, skepticism coming from is I always believed human brains are so special. And then if you look at how the AI models are trained, they're basically simple tensor multiplications and gradient descent. That's pretty much it. And can those simple mathematical operations lead to intelligence and understanding? But the more and more I learn about human brains, I find out maybe human brains are basically doing the similar things, right? We're not that special in many, many ways. That may be wrong. I hope that's wrong, because if that's not, if that's right, I feel a little bit sad for human. And but I don't have a really clear evidence to show like our human brain computation are so special compared to the silicon computation. And then AGI-pilled, and perhaps brain cells aren't uniquely special or complicated. It's basically a biological computer, and all the computation can be simulated in the silicon one, right? Maybe scale is the one that matters, and maybe intelligence is not coming from the really complicated structure of complicated mathematics. It's coming from data interaction. And going back to Rich Sutton and Turing, so this actually solved a lot of my confusion. Is to build an adult's brain, maybe you really need complicated math and so on, a lot of inductive bias. But to build an infant's brain, maybe you don't. And the real magic happens with data and environment rather than with really complicated math. So it's really renaissance with me. I agree with that. And the other thing that happened over the last few years is you constantly observe the impossibilities become realities. Like every couple of months, you think, oh, that thing's impossible. And then a group of people, either externally or internally, just did something that amazed you. And it's just the pace of development is so fast. I think most people outside that world constantly underestimate how things are changing. And there are still many, many open problems. We're going to talk about it in the next part. But I'm really optimistic those problems can be solved in a short period of time. So let's talk about open problems. So I want to define a few definitions just to ground the discussion a little bit, because everyone had their own definition and it's hard to align. When I say AGI, I mean a system can match human level skill across virtually every domain. And when I say ASI, that means that system surpassed best human in every domain. And when I say task-specific superintelligence, is a more specialized superintelligence like AlphaGo, AlphaProof, or OpenAI 5. Those can be the best human in the particular domains, right? And then if you look at the scaling law, some people say scaling law failed, and I have a different opinion on that. I don't think scaling law will ever fail, right? It's just a mapping from the data to the laws. The thing that really failed us is data, and when you cannot get further improvement from scaling law, doesn't mean the scaling law doesn't hold. It just means your underlying data may not be good enough. So that's what I mean by learning is fundamentally data bounded. So how to solve this? One easy idea to try is, we have an infinite amount of compute. Can we convert the compute into data? And for example, in RL you can generate a lot of new data, right? But there are still a few caveats. One is the RL is only limiting the domains where the results are verifiable, like math or coding. So if you look at why people are attacking math first, math is the closest thing to games. It's just a game we invented, right? It's not like physics or chemistry or anything else that's grounded in the real world. Math is basically a game, the axioms and so on, and which is also a fun game, to be clear. Then, the other thing is we're going to see some papers. The current RL, they're not generating a lot of intelligence outside the support of the pre-trained policy. So how to explore new ideas, I think that's also key. The other thing is, then people say, can you just do random exploration? And the answer is most likely no, because unlike the Monte Carlo tracer in Go, your action space is pretty limited, and also anything you do will lead to a win or loss, right? And if you generate random tokens, it's rarely you lead to anything useful. So randomness, you just do random thing will not help that much. And then you ask yourself, how human explore? How new ideas coming from humans? And why, Galois invented group theory, right? Then we want to, this is the first step to address the open problems. One is generating more, better data faster. So then we think about how humans generate data, right? We are first given a task. Our first task is to survive, right? And then to survive, we did a lot of things. It's a meta-learning. And then after that, after giving a task, we learn the existing knowledge. And after that, we think about the problem for a long time and then practice and come up with new ideas. And then we get feedback from the real environment, right? For example, after we invented fire, we will see, is that a good thing or bad thing? Is the food, after you cook, is that better or worse, right? You live longer or shorter. And then we distill that knowledge into the next generation. So we tell them, when you cook a food, you're less likely to die, or you live longer, it's easier to digest, right? And then we iterate. So if you look at the whole chain, where machines can do better, I think for tasks, there are already plenty of tasks, maybe not a good curriculum. For example, in math, there are a lot of, like Riemann hypothesis, right? A lot of those things already. And model can already learn very fast, given enough data. And model can think very fast, but the thing is still, can they explore really, really well? We will come back to that point. And then interacting with the environment, I think that's the key thing. This is also why I'm super excited about AI for science. Is building an environment for AI is actually currently the bottleneck for many domains. Like similar to how humans interact with the environment. Like our intelligence is not only from our thinking alone. Our intelligence as humans are coming from, we think about things and then get reward or feedback from the environment. And then distillation works really well as well. So there's all fast. There's nothing blocking. And the other open question is embodiment necessary for AGI? Like currently, most of the model are not embodied. They're just living on some server side. They don't have a embodiment. And we don't know that yet. But one of the things that can benefit from embodiment is we can automate wet labs with robotics, so that you don't need to leverage your graduate students doing all the hard work, right? And the other is if we can build better digital simulations, that can also work well. Then if you can build anything with simulation, you have a way of converting compute into data, and data is gold. High quality data is gold. So this is focused on can RL generate new ideas? That's a recent paper, I think by Tsinghua University. They're basically saying, oh, we tried some open models, and before RL and after RL, and they compared the pass rate at 1 to like 1 million or something. What they discovered is pass at 1 significantly increased after RL. So basically, they reinforced the correct answer, right? Before, it's getting it wrong, but after RL, when you only have one rollout, it gets correctly. But then they compared the pass at like 1 million or 100K. Then they're the same. Basically means no matter it's base model or RL model, when you have enough rollout, there's a chance the chance that you get it, one of them getting correct is the same. So basically this paper is saying RL did not generate new ideas. They basically made some of the correct ideas more likely in the model. And from their study, this may be true for a particular model, but I personally believe there are way better ways we can do RL that improve upon this, right? This is a good paper to read, and but I'm confident we can have ways to do better exploration to overcome this. And this is exploration in RL, right? And this is something I really believe in. I think most of the human exploration actually only coming from interpolation and extrapolation. It's like rarely maybe their genius is coming in, right? Like Einstein, they invent something totally new. But most of the research are done by interpolation and extrapolation. And what do I mean by that? Like think about in math, the last universalist people say is Poincare, which is like at least 100 years ago. I don't know exactly. But if you look at the current researchers, right? The model now has so much knowledge about everything. Only interpolation can maybe generate a lot of novel ideas, and then you can also do a little bit of extrapolation. So that exploration power keep compounding is already much more powerful than human in most cases. So that's one of the reasons I'm pretty optimistic about RL and exploration in RL. So there's also concrete proof of this. There's a recent paper like 2 weeks old that's called Alpha Evolve. And if you haven't read it, I strongly encourage you to read it. So they improved a lot of mathematical open problems. For example, there's I think when I was an undergrad, I was trying this for a while. The 4x4 complex valued matrix multiplications, right? The state-of-the-art algorithm was like 50 years old. It's from 1969. And then you feed that into models, and then through iterative exploration, learning, they actually find a better algorithm than that. Human has spending 50 years, maybe not a lot of human, but some human, like generations, right? Spending 50 years, didn't find anything better, but the AI found something better. And I think this really gives me hope. The reason I studied math is like in my college, Professor Huang started a seminar called the Galois theory. That moment, like finished that seminar, is the moment I decided I wanted to pure math. This is just so beautiful, so elegant, right? And then my dream was maybe one day I can solve the Riemann hypothesis. And after I go to graduate school, I realized that's not going to happen, and I'm not built for that. But now I'm more confident. Maybe we can train an AI to solve Riemann hypothesis. It's much more feasible than having, me or anyone else solve the Riemann hypothesis. So this is not an exaggeration. I do believe that. I think it's actually going into that direction. And the second bet is, remember, we're fundamentally data bounded as open problems, right? One is you can generate more data. The other thing is we can actually improve the data efficiency in learning. Like, what if you don't need that amount of data to learn well? So there's not a lot of good research around this direction yet, as far as I know. But if you think about fundamental reason why the models need that amount of data to learn, like we can learn as an adult brain, we can learn to play a board game reasonably well with maybe 1,000 tokens, right? The model maybe need millions of tokens to play the game well. And also, the SOTA model are either need to train it or in-context learning that. For human, most of the in-context learning are enough. And then one of the fundamental reasons I think that may be happening is, one is human reasoning is super generalizable, right? We learn to reason, and then we can maybe your learning in Sudoku help your learning in the board games, right? And the other thing is, we do not learn by predicting the next tokens. We do learning by prediction, right? But we do not predict the next tokens. The difference between that is, predicting the next tokens, you are trying to learn a lot of auxiliary structure. Like, there may be a million different ways to say one thing with the same meaning. As humans, we learn more abstractly. We learn the concept rather than learn the exact wording. So if the model is spending so much effort learning the exact wording, that's a waste of compute, a waste of parameters. So that's a fundamental reason why the model is less data efficient. And so this, maybe bottlenecked by that. There's making the reasoning more generalizable, similar to humans, and so on. Time. Cool. Let's and then the next open question is next scaling paradigm, right? We had a few scaling paradigms now. Maybe we want to scale the number of tools, or scaling self-play, memory, lifelong learning, and so on. Those are really good directions to pursue and to try. And another open problem remaining is safety. There's 3 levels of safety, right? One is the model will generate some bad content. This is very similar to the traditional transaction safety for like Facebook or YouTube and so on. The second one is, bad actors leverage models for harm. And I'm pretty confident the first and second thing can be, handled pretty well when we already have a good solution for that. The third one is more existential. Basically, what if the model itself becomes really bad and become misaligned? And especially once become embodied, and they can build data center themselves, they can replicate themselves. And that's one point I think we need to start to worry. We need to make sure this align with our human values, right? And it's a really hard problem because when we say alignment, it's an easy word. Oh, we want to see if the model is aligned or not. But the question is aligned to who? And there's 8 trillion people in the world. So it's a hard problem in many, many ways, many levels. And I hope people will get excited and work on this. This is really important area to work on. Okay, let's on to the future. So I really like a quote from Sam. He said, "The days are long and the decades are short." I never understood that when I was younger, but now I do. I think if you look at what happened for the past decade, you will be amazed how many things achieved, right? Most human beings, and because our intuition, we usually overestimate things happen in the short term. Like we will say, oh, in the next year we're going to solve this and that. But we also usually underestimate how fast things are going in the medium to long term. Like if you go back to 10 years, I don't think people ever imagined we're going to be here, like at this stage. And so here's my hypothesis. Generalizable human prayer plus unbounded computer RL plus a good environment equals super intelligence in any field. You can hold me accountable for this. And so in the future, a few things I'm really excited about, right? One is agent. I think reasoning basically enabled agents, and it's going to be super reliable, it's going to be everywhere, and every domain. And this is pretty obvious in many, many ways. And also, we pretty much know all the research know-hows. It's basically an execution problem. There's not a lot of research uncertainty around it. AI for science is something I'm super excited about. I think one quote I really like from Newton, you can read it here, really touched me. It's like, science, maybe I'll give people a minute to read it. Yeah. I think science is fundamentally a search problem, right? There's a vast search space, and it's a massive search space. You want to find something that's useful for you, relates to your area of research. And this Mu-37 AlphaGo we mentioned before, it's really, if we have that moment for scientific discovery, it may be already happening if you look at the AlphaEvolve paper, right? But maybe to a larger extent, maybe more famous, conjectures and so on. And there's also a good quote from Max, who is, I think, the chief scientist from the Isomorphic Labs. So in the future, doing drug design without AI is like doing science without math. I strongly agree with that. I think AI is becoming the new math for most of the scientific domains. And there's AlphaFold, and also material science, and so on, or AlphaEvolve. One thing, I have a friend in David Baker's lab. He mentioned a lot of I was thinking, AlphaFold is just still in this concept phase, right? But he mentioned actually a lot of drugs are in clinical trial already. And one particular kind, I think that's how to neutralize the snake poisons, which are just, from the structure point, is pretty easy. You just cover some certain points in the protein structure. I have no idea what that means. But they know, there's a desired protein structure. They can map back to the amino acid sequence. But before that sequence is basically a really high recall, low precision mapping. You map to like millions of amino acid sequences, right? But then they use AlphaFold to narrow down the search space. You can map back from amino acid sequence to protein, and then compare to the structure that you want. And then they narrow down like from millions of amino acid sequence to maybe hundreds. So that actually you can have your graduate students do the experiment in the lab and find out the ones that you want. So I think that's one thing AI can do, is really massively reduce the search space. You have a really big search space, use AI. Or you have data accumulated, or you have a simulator, right? Use AI to reduce that search space to like several order of magnitude. Then I have a conjecture also on AI for science. There are a lot of specialized models now for each science domain. Maybe in the future we have a more unified architecture and a unified model that serve a lot of the subjects. And so if you're excited, this is a really good model to build for the science community. I think for math, physics, if you follow Terence Tao's Twitter, he's basically using our models all the time now. He's a really good research partner, and so on. And AI for enterprise is going to be huge. I think similar to science, AI is going to fundamentally lift the ceiling for the R&D for enterprise. And it's also boosts the productivity a lot when you have all the agents in enterprise, right? AI for education, that's something I'm extremely passionate about. I have two young kids, and educate them is taking take a lot of thinking and see what they're going to learn. And there are two things AI can do. One is lower the barriers, and for me, enter to a new domain is always hard because there's a random paper or random thing people wrote on the internet. But AI can make that super smooth. They can make the advanced topics much more accessible to humans. The other is actually AI can raise the ceiling for people who really want to learn. Like I currently use deep research every week, like 10, 15 times. You can I think one thing may happening is rather than doing one PhD in 5 years, you can do maybe 5 PhDs and 10 PhDs, right? If you really, really want to learn. And AI can help you do that very, very efficiently. For healthcare, we mentioned AI just already saved a lot of people's lives, and it's going to be exponentially increasingly so, I personally believe. Most people don't have the really good healthcare provider, and AI is already much better than the healthcare provider most people have access to. Embodied AI, this may be a little bit further away, but there are a lot of hype on this, and it's also fundamentally a data issue. Nothing is unsolvable. Maybe it just take a little bit of time. One is we're still data bounded, And then, how to effectively tokenize actions. All the model architecture for embodied AI is not super well solved yet. It will be maybe in the near future. And also AI devices, right? Think about you will have one AI to talk to that controls all your smart home devices, control, your curtain, right? Your fridge or whatever in your home, your vacuum cleaner and so on, and a dishwasher. This is my dream come true. I think in the future, maybe embodied AI will explore the universe on behalf of human. Like the universe is it's mostly inhabitable for humans, but for embodied AI, it's not. Maybe that's why we're building AI now. That's the future we're looking forward to. That's the end of my talk. Thanks for your time. And you can reach out to me on Twitter or LinkedIn if you want to discuss anything. Thank you.
So we open up for questions. We have a lot of questions. Shuchao, do you want to pick?
Oh, sure. Yeah, go ahead.
Thank you for your talk. It's been very illustrating, very educative, and really great. Thank you. You've talked about a lot of aspects related to learning, like scale, data, optimization. I wanted to know your opinion on the temporal aspect of learning. So far, as far as I know, human brain, one of its main characteristics when it comes to learning is the fact that neurons provide a continuous, discrete electrical signal to all other neurons the whole time. And our models still work as a block somehow. They learn they process the information once at a time. So what do you think is the role of this temporal aspect, or what might it be in the future?
To be honest with you, I don't know much about how brain learns. And I think there will be definitely a lot of differences between how these two learn. And the question, though, in the end is, does the difference matter, or the difference leads to the same learning in some way? And I don't think, it's called neural networks, right? But if you look at really what's happening, the way neural nets learn is vastly different than how human brains are learning. And I particularly myself don't have a goal to really mimic how brain works with neural networks. And it has been working so far. I don't know what's going to be the limit, but as we discussed, I think the way that human brain learns is just super data efficient. Like we don't need that amount of data to update our brain or to think clearly about something. The model still needs a lot of data. I think maybe that's the temporal part is going to be the one of the aspects that's going to help improve. Yeah. Oh, go ahead.
Great talk, by the way. Really liked how you quickly went through from inception all the way to what we're doing today. You shared on a couple of your slides 2 of the bets. You mentioned generate more and better data, and the other bet was sort of vastly improving data efficiency and learning. Yeah. I think methods like program synthesis and things like that are maybe in that second category, where you're trying to be more efficient with the algorithm itself. And then, so what of them among the 2 bets, which do you think is sort of the lowest hanging fruit to go after first? Because on the first bet, maybe we're compute constrained, there's a lot of data behind corporate walls and things aren't annotated, so it's difficult that way. But on the programs or on the other side, it's also difficult. So which do you think is the first that will
I
get?
personally think the first one is a lower hanging fruit than the second one, because the second one requires something much more fundamental change to the existing architecture, to the existing paradigm. The first one, I think in the existing paradigm, the ceiling is already super high. There are a lot of open problems we discussed, but I'm not saying those open problems will necessarily stop us from achieving AGI. They may potentially, but the ceiling for the existing paradigm from what we know is already super high. We're just scratching the surface right now. Oh, go ahead.
Question here.
Oh, sorry.
Hi.
Yeah.
Thank you so much. This is very inspirational and informative. You laid out a vision that sort of compare human intelligence with artificial intelligence.
Yeah.
Your sort of argument is that sort of data is sort of one of the key bounded issue, and we have to. And the assumption that you have is compute and energy will be almost abundantly cheap and available.
Yeah.
On the compute side, I might agree with you because it's more on the digital space.
Yeah.
I'm not sure, especially given this country's energy policy and infrastructure, we will be getting there quick enough to be energy will be cheap and abundant and everywhere available. So my question to you is, how are you or perhaps your organization thinking about strategies to keep that as a risk factor and alternative ways to achieving that?
I think I'm more there will always be barriers to generating more energy, right? I'm optimistic because once we see value, I think society figure out a way. And in terms of OpenAI, I cannot speak for OpenAI, but in terms of the public news, I think Sam is working with the current administration on a lot of new data centers and a lot of new power plants, right? And the power of those data centers. So I'm not naively optimistic, but I am optimistic in some way that we're going to figure this out. Sorry, that's a lot of questions. Yeah, maybe you just go out in order in some way. Yeah.
Recent presentations by Jan LeCun has suggested, in which he has suggested that large language models are inherently limited due to the fact that human knowledge and reasoning is not strictly limited to language. And he's also saying that we need models like you were suggesting that interact with the world, and he calls those world models.
Yeah.
Do you believe that large language models are inherently limited to some very useful applications, but inherently limited in dealing with human knowledge and reasoning?
I think to a certain degree. Like if you go back to the open question, one is, do we think the embodiment is necessary, right, for AGI? And it may, right? It depends on how you define AGI. But the reason why embodiment progress is not as fast as we want is we don't have a perfect word simulator. Like Jan LeCun's point is, if we can build a word model, like a robot can simulate in there, then we can make way faster progress there. And we don't have that yet. I agree that's a limitation. But the thing that I do not agree is, even without that, just in the current limit, I agree that's a limitation. But even within the limitations, the ceiling is still super high. There's so many domains that can benefit from AI, haven't got even started yet. So there are always going to be limitations. But if they say we're currently, how we utilize AI is here, and the potential AI within that limitation is here, and then the gap is huge. And then maybe with limitation, with lifting that limitation, the capability is here. It doesn't really matter how big that is. This matters is this gap. Sorry, go ahead. Yeah. Yeah.
Thank you for your talk. It was really good. You highlighted the importance of data when training our models, and with the exponential use now of AI-generated content, do you think that models will poison themselves because of the new AI-generated content? Is it going to be a challenge for the future?
I think it will be a challenge. I wouldn't use the word poison, the model itself. Like, that's how we also generate a lot of bad knowledge as human beings, like, in case you didn't notice. And we somehow manage to avoid that, right? I think models will avoid that as well. Yeah. Go ahead.
Thank you very much for the talk. So I'm particularly curious about your AI for science part. So recently, we, with Lina actually as well, collaboration, we released 3 AI agents for science, so for more for neuroscience and biology. And one thing we noticed while building this system is that although sometimes the models are really good at solving a specific problem, they're sometimes not that good at following the instructions when there's a complex tool calling involved. So if there is like a task, okay, here's a data set, knockout mice, wild-type mice, please do end-to-end analysis. Often we see models failing at the first step, but if we say, okay, proceed with the next step, they are able to solve it. So do you think that these models for science, that for AI agents for science, would need to be trained differently to be able to follow these complex autonomous instructions? Or you think as the models are getting smarter and smarter, they will be able to?
I think those are very solvable problems as the model getting smarter and smarter. Mm-hmm. There are nothing inherently preventing the model from doing that. I think it's just mainly how much effort people spending on improving the model.
Thank you.
Go ahead.
Thank you for your talk. You mentioned at some point that large AI models can be like as skillful as a doctor, and I'm kind of skeptical about it because there are all these regulations about the data that are being involved in some in this kind of research. So how do you bypass this obstacle and you are able to make such a good model?
I think one point I want to make is rather than replace the doctors, I think it's going to be doctors using AI more efficiently going to benefit the society more. And so there are always going to be regulations. One thing we can see people doing is they actually use AI themselves. Like they are the tool, and the users themselves are uploading all their medical history there, and there's no regulation preventing that. And the other thing is I really think the medical industry, medical industry is highly regulated, so that means things are moving slower. But there are a lot of doctors already leveraging ChatGPT in their work, and they're making better contributions in that way to the society. So, yeah.
So, given the interest of time, just probably 2 last questions.
Go ahead.
Thank you. It's a very good talk. Thanks. And my question is that not every institution have the resource to train their own model, but they still have to solve their problems in their own niche domain. So how do you see this situation? Like, what should they do in the future?
I don't know. I think this is a very biased opinion. I think every institution just should prioritize. Like, there's never going to be enough resource for everything, right? It's all about prioritization. If people think this is important, they should, buy less chairs and buy more GPUs, and
But I think the question would be like, you see, we have so many interests in the AI at Harvard. Like, how can OpenAI helping us? We want to build our own AI for science.
It's really good if we can, talk about that and how we can more collaborating together. Yeah.
Great, thank you. One last question.
Thank you so much for the presentation. If you were an early stage founder building in the AI native interface space, like what kinds of multimodal primitives would you bet on today? I think we're seeing like a lot of action in like voice, and video is also taking off. There are also businesses that help develop models through like helping solve bottlenecks by like helping with providing training data. I'm curious, like, where do you see the biggest opportunities over the next 2 years?
I think that's a $1 trillion question, to be honest. So if you look at the history of human-computer interface, there are 2 major breakthroughs, right? One is the GUI, and the other is multi-touch. So GUI basically is empowered PC, and multi-touch empowered mobile. And if someone can figure out what's the next human-computer interaction based on AI, that's a $1 trillion company. And I don't know. If I know, I wouldn't tell you. But one thing I think I'm confident is I think voice is going to be a part of that. Our vision going to be part of that. It has to be very similar to how humans naturally interact, right? Yeah. But to the exact answer, I don't think anyone knows yet. Hopefully, people are going to figure it out.
Great.
Thank you.
Let's thank the speaker, Shuchao, again. Thank you. Very inspiring. And thank everyone for coming.
What are your thoughts about it?